Welcome to our webcast, Information Integration and the Industrial Internet of Things. I'm your moderator, Mark Hosky, and I'm happy to join you today on behalf of Control Engineering. Now I'm happy to introduce Dennis Brandl, Founder and Chief Consultant at BR&L Consulting Incorporated, specializing in helping companies use manufacturing IT to improve production, laboratory, and logistics processes. He is an active member of the ISA 95 Enterprise Control System Integration Committee, is co-author of the MESA B2MML standards, and is a member of the ISA 99 Industrial Cybersecurity Standards Committee. Is the former chairman of the ISA Batch System Control Committee, contributor to the OPC Foundation and IEC 62541 standards, and has participated in the development of other industrial standards as well. His column on manufacturing IT in Control Engineering magazine covers IT aspects critical to modern manufacturing. He also has regularly judged the Control Engineering System Integrator of the Year Award contest. I am Mark Hosky, webcast speaker, moderator, and content manager for Control Engineering, covering information integration and other control and automation topics since 1994, and writing and editing about industrial technologies and topics since 1987. Today I'll present Control Engineering research results on these related topics. We'll show Dennis's contact information again at the end during the Q&A session. You can submit your questions for Dennis at any time using the Ask Questions console. And now, Dennis Brandl.
Thank you, Mark. I appreciate it. Now, what we're going to talk about today is what IIoT, the Industrial Internet of Things, means in the industrial automation context, and how it's going to integrate all the information used in a complete facility. One of the things is how it will change the industrial automation systems that we currently use today, how to identify some of those opportunities and benefits that are going to come as a result of integrating all the information in a facility, and using IIoT design systems. And more importantly, understand what the future information architecture is going to be in this industrial Internet of Things world that we're moving into, and how it's going to differ from what the current architectures are that we are using. Now, I don't know about the rest of you, but I get usually every day 3 or 4 emails talking about the Internet of Things and how it's going to change, and some of them are the Industrial Internet of Things, and some are just the Internet of Things. Everybody seems to be jumping on the bandwagon, making sure that they are not left behind. In addition, there are conferences and webinars that are going on, multiple governmental efforts in Germany, the United States, China, France, Japan, and others, as well as standards organizations, ISA, IEC, ISO, IEEE. Everyone is working on it. No one wants to be left behind. Everybody sees that there are signs that something real is happening. We know it's going to happen. We know it will make a big difference. But today, it's pretty much anybody's guess as to how this is actually going to occur. So what I want to talk about some is a belief of how this is going to occur. But before I go there, let me talk a little bit about why this is happening. It's a convergence of capabilities that we currently have. It's real because Moore's Law has finally reached what we call real tipping point, where our capabilities to produce inexpensive and powerful semiconductor devices has really started to match our imagination of what we can do with these things. You can easily imagine today some mosquito-sized drone that has video, audio, and enough smarts to map its own path. Those things are existing today in the labs. Or a smartphone that we all carry around that doubles as almost every electronic device that you ever had from less than 10 years ago. This is combined with Metcalfe's law, which states the value of a network increases as the square of the number of devices. And we're talking about billions of connected devices. We have today about 5 computers per person in the world. In the industrialized countries, the typical person will interact with about 50 computers in a single day. That's in their home, in their house, at their work, 50 computers. In the near future, there will be hundreds of smart devices for every person alive. So we're at these inflection points today with Moore's Law and Metcalfe's Law, which probably means we'll only see about another 100 to 1,000 times improvement in both of those areas. But that is quite a bit of capability improvement that we're going to be seeing. And the reason that this is coming so suddenly, apparently, is as a result of exponential growth. It's not common sense. If you remember back in your old high school math days with a math test that said if it takes 10 days to cover a pond with lilies and they double in number every day, on what day is the pond half covered? If you didn't use math, you would say on the 5th day. If you understand math and exponential growth, you knew that it was on the 9th day, the day before the last, because we're not used to thinking about that. That's not common sense. Yet this is the exponential growth that we are currently seeing. We're seeing it in memory capability. We are seeing it in transistor count on microprocessors. We're seeing it in bandwidth capability. There's a quote that I have, I'm paraphrasing this, from Charlie Cutler, one of those legends of industrial automation and the inventor of dynamic matrix control, and he had said, what we wanted to do in industrial control has not changed in decades, but our expectation of being able to do it has grown exponentially. So we've always wanted to do this, but we never thought we would be able to do some of these things. We've gone from 10 megabit networks to 10,000 megabits or 10 gigabit networks in less than 20 years, 3 orders of magnitude. Transistor sizes have shrunk so much that the biggest problem is figuring out where to put the pin connections on a chip. In the next few years, for just a few dollars, you'll be able to buy enough computing power to run an entire production line or even an entire refinery. So imagine where we will be in 10 years with exponential growth. It's difficult for us to imagine, but it is happening, whether we want it to or not. Basically, what we're going to end up with is that everything is connected and everything is smart. Now comes the critical question that we have. If everything's connected and everything is integrated, what does it mean for the future of industrial controls and manufacturing operations? A smart plant, a smart production facility is going to have computing resources that we can't even imagine today, where we have PLCs and DCS systems sitting inside there. And it's not just the basic control, the on-off control, the PID control. There's control at all levels. Using the ISA 95 model, there's control at all levels that run inside a manufacturing facility. So what I'm going to show you is a vision. This is really my vision, but it's based on a lot of discussions with vendors, end users, researchers, and information provided in conferences, webcasts, papers, interviews, the over beer discussions you have with very smart engineers and others. And this is a view of what's going to be happening in the future and how you're going to be able to prepare for that. Well, in order to talk about something, we have to name it. So I've come up with a little name for it, and I'm going to call it a DICE device, which is the smart device. D means it's distributed. It can participate in a distributed information management strategy. I is industrial, meaning that it will follow all the industrial standards that we currently have out there for safety, security, control, device management, communications protocols. And it's control-enabled. It's able to participate in distributed control strategies. So distributed information strategies and distributed control strategies. I'm just throwing this term out there so that we actually can talk about it in this discussion. Okay? I've used the term DICE device to indicate a smart device that is connected, that does participate in information integration and control and configuration. Now, just like any of these things that have seemed to appear suddenly, such as fax machines, which appeared suddenly and everyone had one, there was a lot of development that went on prior to them actually exploding out and becoming very popular. Years and years of development. And this is exactly what we're seeing here in the DICE devices, the IIoT devices, where the I stands for following industrial standards. We have IC 1131-3 programming for discrete control. We have 61512 or ISA 88 for procedural control. We've got security 62443 for industrial automation and control system security. We've got standards for FDI, field device integration, alarm management. All of these are really the basis for the industrial Internet of Things. They don't necessarily apply when we're talking about the Internet of Things for consumer products, but they do apply in the industrial environment. We combine those with the general standards that exist, the Ethernet standards, the 802.x, the TCP/IP, HTML, XML, SOAP, etc., and all of those other standards out there. These are the standards that these devices will follow. So there is a long, rich history of us understanding what it takes to do industrial control, and we're going to use that long history as we move forward to these intelligent devices to put many of the concepts that are in there into these very small, very distributed devices that are out there. There is a term that's being used in the Internet of Things, and they're calling things cyber-physical. These are things that are pieces of equipment that are not just mechanical, such as a motor, or electrical, just such as a motor, but also contain smarts. So the term cyber-physical has really come up. In the old ISA 88 days, we called these equipment elements. We didn't have a name to describe it. I like the term cyber-physical. It implies that there's a physical side and that there's a cyber side on it. All these devices in this coming IIoT world are going to be connected across Ethernet of some form or some manner. Because they're going to be connected across Ethernet, they have to have CPUs in them. That gives them a lot of memory and power. Even the smallest single-point device is going to have a lot of capabilities simply because it's going to be cheap. It's going to be pennies to actually add these to think of a push button, think of a simple limit switch, or think of a more complex switch, some sort of position sensor. Any of these are going to have a lot of capabilities, like 2 gigahertz multi-core processors, a gigabyte of memory, 10 to 100 megabytes of network throughput, be running multiple protocols on the Ethernet, having a real-time virtual machine operating system in there. So it's a single-point device with the power, memory, operating system, and network capability of what we would call a very small, lightweight cell phone. But this is only going to cost pennies. And we're going to have this capability on every device in a facility. Limit switches, proximity switches, motors, pumps, valves, could be all the way down to single points. We already have this capability. We have 10 times this capability today on the smartphone that you carry around in your pocket. So from a physical standpoint, we don't have an issue. From a computer standpoint, from a technology standpoint, a semiconductor standpoint, these things are going to happen. What it will happen is we're going to also have a distributed information environment where every device participates in distributed information management. One of the things to think about, if one of these devices has a gigabytes of memory and it's sitting on a limit switch or a proximity switch or a motor, that 1 gigabyte of memory is quite honestly enough to hold the entire control system strategy definition of an entire facility. The way to think about these devices, the IIoT, the DICE devices that I'm talking about, is that each one can contain the entire strategy, the entire configuration of the system, the entire control system configuration, all the roles, the history, the tracking, every one of those, because there's memory in there. Just like a cell in your body contains all the rules required to build a person or an animal or any other living creature, so each of these smart devices could contain all the information required to recreate the software environment and the configuration environment of the systems that are coming. Because they'll have 1 to 10 gigabytes of local memory in there. They'll have computing power able to do that. Basically, everything you keep today in a centralized SCADA system or document management system or centralized databases can be replicated and maintained in these devices so that these devices can operate whenever they're disconnected and can help participate in this distributed information management. But the real key in the industrial world versus the consumer world is this ability to participate in real distributed control, in a fully distributed control environment where any segment of a control system can be located on any device. And if each device contains the entire control strategy, it basically simply needs to be told what role it's performing and will execute the part of the strategy. Now, this is not rocket science. This has actually already been developed in some of these industrial standards that I've talked about, such as the 61158 Foundation Field Bus discussions, 61804 Function Block Programming, 61131 Program Segments, 61512 Control Module Concepts. All of these talk about how you take a control problem and you're partitioning it to make it solvable, but that same partitioning allows you to put these into the smaller devices. So now we've got a system that is made up of a collection of these devices. They're all talking to each other. They're all executing their strategies, and they're communicating back and forth. Previously, we've never even been able to imagine that we could do this, simply because the networks were not fast enough. The devices wouldn't have enough computing power, or they would cost so much we could not afford to do that. But because of the exponential growth issue, we can now afford to do this. We now have the computing power, and we now have the network throughput to actually talk about fully distributed control, a concept that has been around for 30 years but has never been able to be implemented. Now it can. Now, I just want to point out that we do have a lot of dumb devices, for lack of a better word, today in our industrial systems. So I'm sure what will happen is that there will be a lot of plug-ons that will take and plug a device controller onto a dumb device so that it can participate in this role. And we're seeing a lot of that today with things such as the Field Bus Foundation and the add-ons to those sort of devices. The other thing that makes it really interesting, and one of the more important benefits of it, are auto-configured. If you're familiar with it, ExxonMobil had laid out a diced model of auto-configuration, and yes, there's a similarity of names to what I'm calling the dice device, but then there's only so many letters in the alphabet. So let's imagine configuring a system with thousands of dice devices, or tens of thousands in a refinery or a chemical plant. That could be a very terrible task, but it doesn't have to be. If each dice device has the entire configuration, when a device is replaced, it can pick up its configuration from its neighbors. All it needs to know is what role it plays in the control strategy. I'm pump P101. I'm valve 101. I'm position sensor PS23. By knowing the role and talking to the neighbors, it can pick up all the information it needs. We don't have to manually configure each of these. And this model allows some full simulation. So you can talk to the device and say, okay, I'm not connected yet. I want you to simulate the action so that if I give you a control signal, you'll run your simulation. We can run entire control system simulations offline without having to do anything special. And again here, as I said, this is the cell model, where the cells in an animal pick up the role from their environment, and then each cell contains the entire instruction map. This is where we're going with these devices because it's not going to cost us much to do that. We are going to be able to do this in an environment where the cost of adding this memory, adding the computing power and everything else is going to be pennies on the price of the individual devices that we're talking about. Another concept on it, and this one adds a major benefit, is the concept of adding virtual machines into each of these devices. So I'm talking about here with a microprocessor or a processor that's sitting on a push-button or proximity switch or a motor, but it's really running a virtual machine environment, which means that it can run multiple things at the same time. If you can run one or more virtual machines to run different control strategies at different levels. I'll show that in a minute. Or one or more virtual machines running in a standby or a shadow mode. And the idea here is really to support the patching and the updating, which is the bane of industrial automation systems. It's the real problem in industrial automation systems because you have to shut things down in order to patch. How many of us are behind on our Microsoft patches because we can't afford to shut the system down? Well, with virtual machines, you can patch the shadow machine, make sure that it is running, run it in some sort of shadow mode where it's checking its outputs to make sure that things haven't broken, and then in one cycle switch over from the shadow to the actual machine. We can have zero downtime patching and updating. Now think about this. Today, our biggest problem is whenever we want to do an update, we have to do a big bang update. We have to stop the system. We have to rip out a PLC. We have to rip out a DCS system in order to get additional capabilities. Well, in this kind of environment we're talking about, that additional capability can be downloaded to the virtual machine environment and then just switched on. Or, because if you think about the fact if I pull one device out and replace it, I may be replacing it with one that has more memory, a faster CPU, etc. So I can incrementally improve my control system, just the same way I can incrementally improve the rest of my industrial system. If you go to a refinery today, the valves, the pumps, the motors, etc., and all those, over 20 years, everything gets changed. You don't have ones that are in there that are 20 years old, yet your control system is, because it costs so much to replace it. This gives you the capability of incrementally replacing and incrementally updating all your industrial control systems the same as you do maintenance on any other device and any other piece of equipment in your plant. This is going to be a big change because it really does save a lot of time. So what's running in these little devices, these DICE devices? Not just level 2 controls, but there's all sorts of other control strategies at higher levels that can be distributed. Level 3 control is usually procedural control. It's workflows, includes dispatching, product tracking and tracing, configuration management, etc. All these other workflows that are going on. Well, can these run in a DICE device? Why not? Why don't we look at it? Because let's take a look at these kind of level 3 controls that exist. People are using the ISA 95 models to define the levels, and many people are saying that these don't apply as we move into the IoT world, or the Industrial Internet of Things world. But the bottom line is that these activities still have to occur. The 95 model is really technology independent, but a lot of organizations use them that way. And traditionally, it's because one system handles a few activities. So one system handles all of the scheduling, all of the dispatching, all of the data collection. The DICE devices today really give us a way to change that entire mapping. Doesn't change the activities because we still need to perform those activities inside the system. But what it does give us that capability to do is provide a different mapping of the devices so that these DICE devices can handle distributed control at all levels. So a single device might be performing the sensing and manipulation of the process. It might be performing the basic control because it's going to be executing some of the control strategy, the PID control, the on-off control, the model-based control, the advanced process control. But it may also be doing the procedural control, the workflow controls that exist for dispatching and scheduling. It may be performing the historian functions. So instead of taking all of the data that you have and pushing it up into a data historian, you let the devices collect the data and then only publish them up at a lower frequency so that you have better use of the bandwidth, and you can do the filtering at the low level. So if values don't change, you don't have to actually send them. You can do the same with tracking. So let's imagine instead of a system being made up of sensors, actuators, and then PLCs and DCS systems, and then sitting on top of that, MES systems and historians, and instead talk about an environment where this is basically a network of these DICE devices that are out there. There may be DICE devices that are connected to hardware. There may be some that have no physical side associated with it. They're just the computing power piece on it. But my control system is running in this distributed environment. And it's very redundant. If one of these devices fail, The worst that happens is that one part of a control strategy fails, versus a PLC. If a PLC fails, everything shuts down. If a DCS or part of a DCS fails, I may lose 6 loops, 8 loops, something like this. Instead, we lose at most 1 loop. So we're going to have control activities. All the activities that we do in manufacturing are going to remain. It's just where they're going to be, how they're executing is a little bit different. Now, you may remember the children's books, the Where's Waldo books that are out there. And in all those, you basically have this big picture, and someplace in this picture is Waldo with his red striped shirt. Well, there's one of those they had, which unfortunately I can't show due to copyright, but basically every character in it is Waldo. And you have to say, where's Waldo? Well, he's everywhere. And I think that's what the issue is here. Where is Waldo? He's everywhere. Likewise, in the new system, where's the controller? It's everywhere. The controller exists as a distributed environment in the entire system. You can query it because every node knows what the control strategy is, so you can talk to any node. You can find out what role each device has, so you know what role it's performing. But if you look at it and say, where's the control? It's like looking at your brain and saying, where's the consciousness? It's distributed throughout all of the neurons and all of the control systems that are out there. So where's Waldo? He's everywhere in those pictures. Where's your controller? It is everywhere in that picture. So in summary, what I'm talking about here is that IIoT, it doesn't change everything. We still need to perform the basic activities that we do in manufacturing. What it does change is where is it occurring. And it lets us do things we can only imagine. It lets us do things such as have incremental additions and improvements in our control strategies without having to go out and replace brand new PLCs and DCS systems. It basically means that the PLC, DCS control vendors will become a lot more software vendors and probably sell the smarts and the software that will run inside these devices to handle the control strategies. It provides this capability for zero downtime patching and updating, which means we'll have much more secure systems in there and nearly infinitely extensible systems. So again, to repeat what we've been talking about here is what we've wanted to do in industrial control has not changed in decades, but our expectation of being able to do it is growing exponentially. We have higher and higher expectations that the things that we've always wanted to do over the past 30, 40, and 50 years, we are finally able to do. And that's the world that we're moving to in this industrial Internet of Things. And now I'm going to pass you back to Mike Husky.
Thanks, Dennis. Nice going. It was a great perspective on how it all fits together. For my part, I'm going to review some trends on control engineering, information integration research, industrial Internet of Things, and Industry 4.0. I'll quickly cover the methodology for the research and one slide on the respondents' profiles, and then I'll look at the perceptions of and spending and benefits and challenges of IIoT and Industry 4.0 implementations. And then I'm going to cover how effective information integration has been. Information integration is a key aspect for both platforms. A series of webcasts and articles from Control Engineering and other CFE media publications provide more about the IIoT and Industry 4.0 platforms. Here, though, I'll focus on a related Control Engineering research report just completed in November. Here is the introduction and methodology for the report. Key takeaway here is that margin of error is little over 4% with the sample size. Keep that in mind as you see results that are close in percentages. Many of these slides are rich with information, and some of my analysis adds to the obvious on the slide. So I may pause a moment after each slide to help you absorb the information. There's a lot here. Among the areas the research covered were familiarity with IIoT and Industry 4.0, funding, product areas, and differences between them. Information integration and topics include integration among levels, reasons for lack of integration, perceived information integration benefits, and challenges of information integration. I'll go into some of the research now. The full report will be linked to the archived webcast and on the resource page at the end. We looked at the profile of the respondents several different ways, and more respondent details are available with the full report. Here, note that the top 3 industries represented by respondents are instrumentation, measurement, or control systems and devices at 31%, engineering, system integration, and architectural services at 29%, and consulting, business, and technical services at 24%. After that, industry involvement steps down by 1 or 2 percentage points across 15 other major industry groupings. The research is split into 2 sections. First on IIoT and Industry 4.0, then on information integration. Despite heavy coverage of these topics by control engineering and other publications, it would seem that even more coverage is needed, with more than 40% of the respondents not very or not at all familiar with IIoT, and more than 65% not very or not at all familiar with Industry 4.0. Somewhat familiar was the largest topic for IIoT, and not very familiar was the largest topic for Industry 4.0. 15% or less were very familiar about either platform. We prompted survey takers by listing major attributes of IIoT and then asked them to rank how useful each of those attributes were. Interoperability and open standards and security were the 2 most useful, followed by analytics, mobile, and cloud. But even the last 2 on the list, mobile and cloud, more than half the respondents said they were useful or very useful. We also listed major attributes of Industry 4.0 and asked survey takers to rank how useful each of these were. Real-time capabilities and interoperability ranked highest, followed by modularity, service orientation, virtualization, and decentralization. Here again, even the lowest on the list are ranked as useful or very useful by well over half of the respondents. How well are the concepts being applied? For IIoT, security and interoperability were among the most implemented. You can see the respondents felt there is a lot of room for progress. The numbers who are just beginning in these areas are significantly larger than those who have already implemented these concepts. For Industry 4.0, all 6 areas were neck and neck for being implemented within the margin of error. Real-time capabilities and interoperability were making the most progress among all of these. Again, respondents felt that there is a lot of room for progress among all of these attributes. Look at how much larger the beginning group is than the implemented group, almost 3 to 1 in most cases. Do these platforms make any difference in spending? The perception among survey respondents is yes. Anticipated spending increases as a result of IIoT or Industry 4.0 averaged a little more than 30% from 2015 to 2016. This seemed extremely positive to me. Where will that money go? Areas of improvement for that spending are led by human-machine interface hardware, computers and industrial controllers, programmable logic controllers and programmable automation controllers, software, and wireless infrastructure, followed closely by process controllers, process sensors and transmitters, and other areas. So interaction with information seems most important through HMI. Processing and analysis are important with controllers, computers, and control systems. Information and data transfer wirelessly is important. And then sensors and instruments, data collection basically, that's important as well. And then input and output systems, I/O, the connection points, that's also important. We also asked about opinions related to IIoT and Industry 4.0. Many see each platform as different sets of words for what we've been trying to do all along, and many of them see it as two sides of the same coin. Perceptions were helpful, and very few saw them as negative. Comparing IIoT and Industry 4.0, 56% of respondents are using or planning to use elements of each platform. More lean toward IIoT at 20% than Industry 4.0 at 16%, but that's within the margin of error for the study, so really they're just about even. Here's a bit about the study on information integration, a key element of IIoT and Industry 4.0. This is a complex graph, so I'm going to take a minute to explain. Looking at information integration, where level 1 is the plant floor, level 2 is advanced manufacturing control, and level 3 is the enterprise, there are many opportunities for improvements in information integration. Looking at the direct integration between plant floor and enterprise, more than 40% of respondents had little or no integration. Less than 20% claimed high integration or bidirectional flow with frequent use. Even between layers 1 and 2, where one might expect the greatest amount of information integration, only 17% of respondents said that they were highly integrated. Major reasons for lack of integration are that benefits are unrecognized and an unwillingness to assign appropriate resources, closely followed by difficulty and cost of implementation. Perceived security risk was the largest obstacle for lack of integration between levels 1 and 3, more than 1/3 of respondents. Desire to restrict access, also related to security, was next. As for information sharing between levels, more than 1/3 were network connected. But it didn't seem very encouraging to me that 40% or more of the respondents shared information between manufacturing and corporate management via reports with frequency of a weekly or longer. This would seem to indicate that we're a long way from two-way, real-time information flow between manufacturing and corporate management. Integration tools. The 3 top tools or resources used by respondents to establish and sustain integration are system integrators, 42%. That's up from 34% from respondents to the 2014 Information Integration Survey. Customized software was next at 42%, and browser-based interfaces at 34%. Mobility devices and software are next. Only 16% said corporate-only devices, which also might raise security concerns. Top benefits recognized by facilities that have integrated systems were better support for decision-making at 47%, faster decision-making at 39%, better control of resources at 39%, and more automated processes at 34%. Close after that were improved quality and accuracy and higher manufacturing productivity. Top challenges that respondents reported facing when integrating operations were a lack of budget, 39%, confusion over scope and benefits, 36%, training individuals to use this technology and processes, 35%, and a shortage of personnel resources, 34%. About 1/4 also listed the cost of design and maintenance and lack of interdepartmental cooperation. Thankfully, only 7% said initial tests didn't work, although I suppose given the desire for interoperability mentioned earlier, even that might seem too high. The next data set extends over 2 slides, looking at how technologies change workflows. The slides look at, has technology changed how end users work, how technology has a great potential for increasing productivity, and technology, how it will change how end users work. The top 3 technologies across both slides here, so please be patient. The top 3 technologies that have changed how respondents have worked over the past few years are increased process power in PLCs and controllers at 47%, cybersecurity at 43%, and deployment of newer control platforms at 40%, followed very closely by remote information access, increased HMI sophistication, and mobile computing, all within a margin of error for that 3rd spot. Again, continuing on the same information, the top 3 technologies and trends that respondents believe will change how they work over the next few years are 3D printing and additive manufacturing at 43%, industrial Internet of Things at 41%, big data at 39%, although Industry 4.0, mobility, and mobile computing and robotics follow closely on that 3rd spot, all within the margin of error. Looking forward, 44% of respondents reported that integration within their facility will increase at a slow pace. 25% would like to improve, and 24% are currently undergoing improvements for information integration. At the bottom, adding up the last 2 categories, more than 20% already see benefits, which is very encouraging. More results are available in the links on this page, along with connections to related topics. Many thanks to CFE Media Director of Research, Amanda Pelliccioni, for conducting the survey and compiling the report. Now we have a question and answer session. The audience listening live can type the questions for today's presenters in the Ask a Question box on the screen. We will answer as many questions as we can before the top of the hour. Within a few days, the presentation will be available for on-demand viewing along with a link to the quiz for potential PDH credit. We'll post the archive on the Control Engineering website, and we'll send an email message with a link connecting directly to it and to the related resources after it's ready. If you contact any speakers here directly via email, please reference this webcast in the subject line to help ensure that we recognize the email in the correct context. Now on to the questions. So, let's see. What measures are developing to prevent catastrophic data security breach that would shut down operations? Obviously, cybersecurity is a big concern, Dennis.
Yes, quite a big concern, and a lot of work has been going on in the ISA 99 committee and helping develop the industrial standard for industrial automation cyber system security. This work has given us the whole concept of zones and conduits. So as we think about all these IIoT devices that are going to be connected, or all these DICE devices as I call them going to be connected, they're going to be connected inside zones of control where the same cyber system security policies are being implemented. And again, we're looking at one of these things. They have sufficient CPU power. They will probably contain their own internal firewalls, internal antivirus systems, and others that are in there. Then there will be communications between the conduits that are defined in ISA 99. The conduits themselves today are typically things such as routers and switches, smart routers, smart switches. So a lot of the measures that exist today to protect our financial information and to protect other things are going to be existing in the industrial environment as well. And that will help some of the security breaches. The other thing to consider is that we have learned over years how to protect these devices so that somebody can't log in and make changes, so there are authorizations for roles. There's various encryption mechanisms to make sure that the communication is secure. Every one of those things will be applied in these industrial devices simply because we recognize of the financial impact that it could occur and the safety impacts that could occur in case they get compromised.
And we do have additional articles and a separate research study on cybersecurity as well. It's a hot topic. And for people who think that their existing control systems, their old legacy control systems are secure because they may not be connected, nothing is secure anymore. And certainly an updated control system would have a better opportunity to thwart a threat perhaps than some of the older systems that were designed before any of these threats took place. Another question, what are the principal infrastructure aspects to assure that cost savings on deployment and implementation of industrial IoT?
Yes, in that case, the key is to get your infrastructure in place, and your networking infrastructure and your security infrastructure in place, because you're going to be expanding it and extending it by orders of magnitude. So if you have ad hoc policies and procedures to improve and install your infrastructure, those need to get replaced with very specific procedures and policies that allow you to scale up quickly. The primary infrastructure will probably be Ethernet. So we're talking about 1 gigabyte, 10 gigabyte backplanes, network backplanes that will be able to do the switching that we have. Even if we look at wireless and things such as ISA 100 as communications, they still end up going across the Ethernet backplanes. So high-speed switches, redundant backbones of your network, all those have to be in place, and then a very strong security policy to control the access, to set up VPNs, to set up virtual networks inside there, and to control the access to it. Because instead of having to worry about the safety and security of, let's say, 200 employees, you might have to worry about the access of 2,000 to 20,000 devices that you have out there. So your management of those is going to become very critical. And you have to spend a lot of time and effort to make sure that you can scale all of those things up.
And while the architecture will be segmented, certainly you are considering connecting more than just the manufacturing, it's the enterprise and the connected supply chain as well. So checks and balances have to be in place. How would IIoT benefit a company in a developing country?
That's an interesting question, because in actual fact, it'll probably benefit developing countries more than it will the developed countries. And this is simply because the developed countries already have a very large investment in what I'll call the traditional or the classical automation and control environments that we're talking about, the PLCs, the DCSs, and some of the others. As you move to this IIoT world, each device out there gives you the capability of a PLC. If you don't have those in place today, so you're in a developing country, as you install this, you're going to get the benefits immediately. Just like cell phones today in the developing countries are going in much faster than they went into the developed countries, because the developed countries had telephone networks in place, so the cell phones could not effectively compete against them. But when you went into a developing country, you did not have the telephone network in place, so they moved much faster. So I expect in this diced world that we are going to see a lot more implementations of this in the developing countries than actually in the developed countries for quite a few years.
Dennis, there were several questions talking about communications. How are we going to talk about different protocols to be used by IoT? Wireless protocols, Zigbee, Z-Wave. How will DICE devices talk to each other and with connected systems?
Well, as I said, I believe most of these devices will be talking Ethernet, and there's a couple reasons for that. That is really the most scalable network systems that we have out there. With the addition of TCP/IP or of IPv6 addressing, we have essentially IP addresses, several IP addresses for every square meter of land on the entire world. So we are not going to run out of addresses, so it's very scalable. We already know how to do partitioning on it. And it's cheap. The bottom line is that the Ethernet cables, the routers, the switches, because they're used in the consumer, commercial as well as industrial, means that they are significantly cheaper than anything else. So we're going to see those being used, and it's also most standardized. No single vendor controls that. Now, we will see protocols on top of that. You know, today there's multiple protocols. We have Ethernet IP, we have Profinet, and we have OPC UA. I think all of these are going to exist. All these protocols will be communicating. There'll be probably some bake-offs at some point in time here to say who is best supporting the full concept of distributed control and the program distribution, the information management. My feeling, and it's just my viewpoint on that, is things like OPC UA, which are open standards and IEC standards, and support already a lot of the concepts that were in the Field Bus Foundation and a lot of the programming distribution concepts, because they're part of PLC Open, will be one of those that really has moved forward. In terms of wireless, we'll probably have many of those. We'll have to see what happens on the ISA 100. It was designed specifically for the industrial environment, so it has a lot more security built in and a lot more capability for running routerless with mesh networks. So it'll be interesting to see what happens there, but I believe that we are going to be talking about Ethernet and the various Ethernet protocols for a very long time in this area.
Great. We have many more questions, and we're going to try to address those offline. Thank you very much for submitting the great questions. Just as a very quick close, Dennis, for those whose heads hurt now after hearing all this, what should they do first?
The first thing you should do in these cases is to sit down and recognize the fact that we are in the middle of change, that what you see today is not stable, that there's going to be significant changes. And to make sure that if you know that you're going to be involved in this, that you learn some of these technologies, you learn some of the things that are going on. You may not be an implementer, but you should at least be aware of the advances that are going on in the semiconductor industry, in the communications industry, so you're aware of what the capabilities are. The biggest problem we have now is that our capabilities are growing so great that people can't even think about the things they want to get done. They automatically assume it's not done. So stay informed. Read Control Engineering, okay, Mark? And as well as the other magazines out there, so that you can be aware of what's going on, so you'll be able to take advantage of these changes.
Thanks very much, Dennis, for sharing your time and expertise.